So I got n, 2, and 3n, and up to p minus 1 divided by 2n. And I consider these are all my p. And I take the positive residue. So I take everything I take the positive residue. Okay. Okay. Then I just denote m to be the number of this residue, basically the number of, let's say, x in S such that x greater than p divided by 2. Okay, so ask what's how many of this guy where residue is greater than p divided by 2. Then we have NP Legendre symbol will be just minus 1 to a. Okay, so this is the Gauss Lemma, and so this is Gauss Lemma. Okay, so let's go through a proof. Okay, so proof is a little bit tricky. So let me just it's a little bit lengthy and complicated. So I want to like do it step by step so that you guys will not miss. And okay. Okay, so let's consider S, right? S as previous S. Okay, so let's write S. Let's write S into the union of two set, A union B. And let's say A, right? So A is the residue which is less than P over 2. Okay, so A is a set of whose residue, let's say there are M of them. Sorry, K of them. Say K, right? And then for B, you will get M of them, right? Because by definition, M is the number which is greater than P over 2. So I get B1, B2 up to Bm. And then there are disjoint, right? So there are disjoint. Okay, and so I can define C to be C1 up to Cm. And I define C to be just Ci to be just P minus Bi. Okay. Okay, so hopefully this is simple for you. Okay, so the first thing I want to say is that A and C are disjoint. Okay, and the reason is the following, right? So A and B are disjoint, right? But it doesn't mean that A and C are disjoint. Okay, proof. The reason is that right, suppose Ci equals to Aj, that means that P minus Bi equals to Aj. Okay, so that means that Aj plus Bi is 0 mod B. Okay, and we know A, right? A is, let's say Aj just T times some n, right? T is just the number that we choose. And let's say I is maybe S, maybe it's also S times some n. Okay, so this means that T plus S, n is 0, mod P. Right, but recall that I can choose. Recall that we choose, right? Remember that we choose that T, right? We choose our T from 1 to P minus 1 divided by 2. Also, S is from 1 to P minus 1 divided by 2. Okay, so if this is true, that means that P need to divide T plus S. But this is impossible, right? Because T plus S at most P minus 1 divided by 2. Okay, so T plus S at most P minus 1 divided by 2. Right, so this guy cannot contradict this guy, right? So this means that Ci cannot equals to Aj. So they are all disjoint. Okay, so here comes the trick. Since P minus Bi equals Ci and they are all disjoint. So recall, so A, right? A is the residue less than P divided by 2, right? So this is 1 and the P minus 1, right? And the P minus 1 divided by 2 and the P divided by 2. So these are all the number that A sit. Okay. And since I'm just using P minus Bi equals to Ci, right? So B is a number sit inside here. but I use P minus BI equals to CI, right? So that means that C is also inside here. But since they are all disjoint, and so A and C are disjoint, right? And the number of A plus the number of C is exactly what? It's P minus 1, right? Because I total just got that P minus 1 number, right? Oh, sorry, I just total got like P minus 1 divided by 2 number. So this means what? This means what? The A union C will just be 1 to 2 up to P minus 1 divided by 2, right? Exactly. And they're all distinct, right? So A union C is just a set of these. Okay, so this basically finishes the proof, right? Because let's write down. So I have A union C will be just A1 up to AK, C1 up to CM. And then basically just the permutation of 1 to 2 up to P minus 1 divided by 2. Okay, so I can get A1 up to AK times all of this, C1 up to CM equals to P minus 1 to factorial, right? By definition. And so this P minus 1 factorial by definition will be just this, right? Let's say mod P. So A1 are just, right? So A1 and AK are just what? Just the multiple, right? Just multiple of this, right? So it will be like 1n, 2n, like 3n, up to P minus 1 divided to n, right? But for this one that I need to times minus 1 to the m, right? The reason is the following, right? The reason is that since this is actually a P minus BI, right? So C is not that something times n, right? But C is P minus BI, so I can mod P, that become minus 1 BI, so it will be this, okay? Mod P. Okay, or let me just write carefully so that you guys will not miss. So let's write this P minus B1, P minus BM, right? So if I mod P, then I can get the A1 up to AK minus 1 to the M, B1 up to BM, mod P. And all this will be just all this A1 up to AK, B1 up to BM by definition, right? Will be just S. So I will get minus 1 minus 1 to m, n to n, p minus 1 divided by 2n, and I can cancel all this vector. So I will get n to the p minus 1 divided by 2 equals to minus 1 to the m mod p. So, and by the Euler theorem, this will prove the np will be just minus 1 to the m. Okay, so this is the Gauss lemma. Okay, so we need another lemma, which then we can prove the theorem. Okay. So the lemma. So m is equals to t and p, and t from 1 to p minus 1 divided by 2 plus p squared divided by 2 divide p squared minus 1 divided by 8 mod 2. Since we only care about mod 2, right? So I only need to compute m mod 2. Okay, so this is the theorem. Theorem tells you that m is equals to this plus this and mod 2. Okay, so if n is odd, then m can be written as t and p. So there's a minus 1 here. So I'm stupid. Yeah. And t from 1 to p minus 1 divided by 2. Mod 2. Okay, this is stupid, right? Because if n is odd, then this guy will be even. Okay, so this is what we want. Very special, right? We're very weird identity, right? Why this is true? Okay. And okay, so proof. The proof goes as following, right? So as I can write t and p to be the integral part plus the fractional part. So these fractional parts will force it to be 0 and 1. And okay, so I can write Tn equals to P and TnP plus I just times P and I call it Ri. Let's call it RT. Let's call it RT. So RT is basically the rest. So RT is just Tn mod P and the positive residue. And choose the positive residue. Okay, so by Gauss, right, the previous proof will tell me that R1 up to R P minus 1 divided by 2 will be just A1 up to AK and the B1 up to BM. And we also have C, we also have 1 to 2 to 3 up to P minus 1 divided by 2. This set is basically A1, AK, C1 up to CM, and the CI is just P minus BI. So we need to use this and then relate M to this. Okay, so this is our proof strategy. Okay, so the proof idea just using the algebra. So okay, and okay. The first equation what we have is I from 1 to P minus 1 divided by 2 will be just sum of A and B, right? So sum of A and B, so I get summation AI plus summation BI. So I from 1 to M, I from 1 to K. And then we have second equation. So second equation is this. So we got sum of like I, right? I from 1 to P minus 1 divided by 2 will equals to summation of AI plus summation of CI. Okay. And okay, so let's say so number second equation can be written as summation of I from 1 to P minus 1 divided by 2. All these turns stupid. So I just evaluate, right? So this can be proved by just 1 plus 2 up to P minus 1. So it's P squared minus 1 divided by 8. Okay. And just equals to AI plus B P minus BI. Okay. And it's just summation I, and then there are MP, right? MP minus summation BI. I from 1 to M. This is I from 1 to K. Okay. And what? So I have this and this, right? Now what should I do? What should I do? Okay, I want to cancel AI, right? I want to cancel AI. So I just add 1 and 2. Okay, so I should get summation of I from 1 to P minus 1 divided by 2 equals to, right? We got 2 KAI. Sorry, it's 2 times I from 1 to KAI. So and plus MP. Okay. And so this just tell you that okay, so let's see. Sorry, stupid, right? So when you add it, you still add. Sorry, I forget these terms. So P squared minus 1 divided by 8. So just add the 1 and 2 equation, and okay. So if you mod 2, right, this guy will cancel. So yeah, so basically it's hopefully this almost finished the proof. Okay, the reason is the following. So sorry, so MP plus 2 of this will equals to this. What the hell is going on? let's see. So yeah, a plus b equals to r. The t and this guy, right, equals to ai plus this. So it's np plus this. So if I add it, then I get ai plus this equals to this equals this. Okay, so this means something, right? This just tell you me that okay, so I can find a, right? So I can just write m. What's this? What's this ai? It seems like I missed some number. I missed one number. I just don't know where it is. Oh, sorry, I'm stupid. Sorry about this. Okay, because R, right? So R is Tn minus P of this, right? So stupid, sorry. So Ri just Tn minus, sorry, RT just Tn minus P, TnP. Okay, if I plug in, then I will get P squared minus 1 divided by 8 plus NT, right? Minus T and P. Let's see it's correct or not. I from 1 to P minus 2, or T from 1 to P minus 2 of this, and equals to 2 of this. K plus NP. Okay, so so what? So this will give us, right? These two terms are actually the same, right? Because if you plug in, you got T, like you got the same, right? So got n plus 1, P minus 1 divided by 8 minus summation T from 1 to P minus 2, T and P and P equals to 2 of this plus NP. Okay, so these are equation. And finally, I just write M, right? If I mod 2 or whatever, right? Because P is odd, so I can mod 2, right? So I mod 2. So I mod 2, this can be M minus 1, P minus 1 divided by 8. If I mod 2, right, I don't care about this. Then I will get the following. So I can minus 1 can be plus. Okay, so just mod 2. So mod 2 is this guy died, and then this guy become M, and then this minus can be plus, and then this one just this. Sorry, and the P just neglect, right? Because P is odd. Okay, so finish the proof. Why is proof so difficult? Okay, so now we can prove the reciprocity law. Reciprocity law. Okay, so this is pure algebra proof. So idea is the following, right? So we know that QP will be just minus 1 to the m. So these things are considered like n is odd, QQ is odd, right? So I have the m beautiful notation. I just TQ divided by P, and T from 1 to P minus 1 divided by 2 mod 2. And I also get sorry, I sometimes you can use this notation, but some people use this notation. So I just PQ equals to minus 1 to n. So I need just SP divided by Q. And then S equals to from 1 to Q minus 1 divided by 2, and then mod 2. Okay, so this proves that, and this product, right, the product of QP and PQ will be just minus 1 to n plus n. So n plus n will be just t from 1 to p minus 1 divided by 2 plus s from 1 q minus 1 divided by 2 s p q and the total mod 2. Okay, so yeah, this is q. Okay, so the final thing, the final just to show. So show what? Show this guy just p minus 1 q minus 1 divided by 4. Okay, so now we have the very, very powerful proof. Okay, so consider following function xy equals to qx minus py. And the x from that's 1 to p minus 1, and the y from like 1 to q minus 1. Okay, so we know that okay, so first notation, the first thing that we can know is that fxy cannot be the same as x. Cannot be the same unless x equals x prime and y equals y prime. Okay, the reason is the following. Since p equals prime, so you can check that. I mean, first you check this is linear, right? So you know the qx x minus x prime minus p y minus y prime. So they are co-prime to each other. So since they are co-prime to each other, right? So they cannot be the same. Okay, so fxy has p minus 1 divided by 2 and q minus 1 divided by 2 values. Since they're all different, so they have all this value. Okay, so the very stupid thing happens, right? So for fixed x, then suppose we have fxy greater than 0, then this just tell you that y is less than qx divided by p, or basically tell you that y is less or equal to qxp. Okay, so that means that when f is positive, then you always have the number of points such that f is positive is just qxp and x from 0 to p minus 1 divided by 2. Okay, so similarly, when f is less than 0, the number of solution will just be py divided by q from y from 1 to q minus 1 divided by 2, right? By definition. So it's stupid. So now we prove the results, right? Because this is just the even part and the odd part. The positive part and negative part. And then the positive value and negative value, the sum of total distinct value will be just p minus 1 times q minus 1 divided by 4. And yeah, so this finished the algebra proof of Legendre, the reciprocity law. Okay, so I think in my video channel that I presented two proof, and hope you guys enjoy this one. And I finish this in the next video. Let me just talk about very simple application, and then we go to like Gauss Sum or more difficult analytic number theory. See you guys next videos.